Okay, so first, these problems are already posted in the problem section on Blackboard. So we will sort together some problems, and after this, I will give you an assignment on problems on 7 and 8. Okay, so we will start by the first problem. We have that a disc of 40 centimeter in diameter and 5 centimeters thick is cast of pure aluminum in an open mold casting operation. Aluminum melts at 660 degrees, but the pouring temperature will be 100 degrees. The amount of aluminum heated will be 5% more than what is needed to fill the mold cavity. So as you can see, always we use additional amount to take into consideration shrinkage. Okay, so here, for example, they gave us the dimensions of the final product, but the volume that will be used will be 5% more because we know that you will have shrinkage during the solidification process. Now, compute the amount of heat that must be added to the metal to heat it to the pouring temperature, starting from a room temperature of 25 degrees. The heat of fusion of aluminum is given to be 389.3 joule per gram. The density of aluminum is 2.7 gram per centimeter cube, and the specific heat is 0.88 joule per gram per degree. So first, here, if we want to do a small scheme about how temperature will vary, okay, what do we have? We have first, we want to heat, we know the initial condition. The initial condition is 25 degrees, and we want to heat to the final temperature of 800 degrees. So when going from 25 to 800, we will go through several stages, okay? So first, when we supply heat to our system, we can draw the variation of heat supplied, of temperature with heat supply, okay? You know first that when going from 25 degrees to the melting temperature, I am in which phase? So initially my aluminum is in solid state, okay? So what I am doing first is that I am heating from room temperature, which is 25 nearly, to the melting temperature. So in a first stage, from 25 degrees to 660, which is the melting temperature, I am doing solid heating, okay? And this is, since I have one phase, then my heat will be in which form? What is called the form of heat in this case? Sensible or latent? If you have taken thermo course, you know that if I have one phase and I heat, okay, this is called sensible heating. In sensible heating, the temperature will increase, okay, and the amount of heat can be calculated by which formula? We have a formula for Q sensible. So Q sensible is given from the mass to be melted times Cp times delta T. This is the formula of sensible heating, okay? Now, in the first phase, I am heating from 25 to 660 degrees. So delta T will be 660 minus 25. And just pay attention for your units, okay? Here, the specific heat of aluminum is given in joule per gram per degrees. So to obtain Q in joule, the mass should be in gram and delta T should be in degrees. So here if I replace to get Q sensible during phase 1, so Q sensible phase 1 is equal to the mass, which I will calculate now, times the specific heat. The mass, I should calculate it in gram, okay? The specific heat is 0.88 joule per gram per Kelvin per degrees. Anyway, if they give you the specific heat per degrees or they gave you the specific heat per Kelvin, delta T is the same. You know that delta T in degrees is equal to delta T in Kelvin. Why? Because you have a just a constant difference between them. We know that T in Kelvin is just, so T Kelvin is equal to T in degrees plus 273. Okay, so if you calculate delta T in Kelvin or in degrees, it's the same value because this constant will be subtracted, so it will not affect your result. So now here, since temperatures are already given in degrees, so delta T is 660 minus 25. Now, in order to be able to calculate the mass in gram, I should find what is the volume of molten metal. Okay, they said that the amount of aluminum heated will be 5% more than what is needed to fill the mold cavity. So your final desired product is a disk of 40 centimeter in diameter and 5 centimeter in thickness. So if I want to present the geometry of the final cast, it is like this. I have the thickness, it's provided, and I have the diameter. So I can calculate the value of the final volume, okay? And once I know the final volume of my casting part, taking into account shrinkage, they told me that I should use 5% more volume than the final one. So here, the casting volume should be calculated because I know the dimensions. So I have D equal to 40 centimeters, and the thickness is given to be 5 centimeters. So I can say that the volume of molten metal, okay, V molten metal, should be equal to V of the casting, the final casting, okay, times 1.05, because I should add 5%, okay? Now, what is the volume of the final casting? It is pi d square, pi times d square over 4 times the thickness. Okay, this is the volume of the final casting part times 1.05. And since the dimensions are in centimeter, I will get my volume in centimeter cubed. And as you know, I want to obtain the mass of molten metal in gram. To have the mass of molten metal in gram, I should multiply the volume by density. And since I need the mass in gram, and the density is in gram per centimeter cube, so the volume should be in centimeter cube. So now to get the mass in gram, all I have to do, so the mass in gram is equal to this volume I calculated, V molten metal in centimeter cube, times the density value, which is 2.7. And the unit is already good because I want the mass in gram and I have the volume already in per centimeter cube. So it's 2.7 times gram per centimeter cube. The resulting value will be in gram. The mass will be obtained in gram. So now, once I get the mass, I can replace back into my equation and get the sensible heat of phase 1. Now, to continue the heating process, what will happen now, once I reach 660 degrees, which is the melting temperature, I will have to maintain this temperature until complete change of phase. Because here, at the beginning of the melting phase, I have 100% of solid. So now the heat that is absorbed will be transformed into not sensible heat, latent heat. What do we mean by this? The temperature will not increase, but what will happen is that the energy will be used to transform the state of my system from solid to liquid. Why I need energy to go from solid to liquid? because you know that solid bonds of molecules in solid states are very strong. If I want to go to the liquid state, I should do a rupture of these bonds. And to do rupture of these bonds, I should provide enough energy to molecules to do certain separation from each other. Because you know that in a liquid, the distance, the relative distance between molecules is much larger than the relative distance between them in solids. Because you have stronger bonds in case of solids. So to have this rupture and higher freedom of molecules, I need to provide energy. This energy is called latent heat of fusion. It is the energy needed to go from 100% solid state to 100% liquid state. If once I provide the whole amount of energy, which is called heat of fusion, I will go from 100% solid to 100% liquid. And this phase two, in this phase, I say that heat is provided in the form of latent heat, not sensible heat, because sensible heat is seen in change of temperature, while latent heat is seen in change of phase. So now I can say that in phase two, so in phase two, I have latent heat because I have change in phase. Okay, latent heat due to change in phase. So now the resulting value to calculate it is, I know maybe if you didn't take thermo, you don't know these formulas, but you will just be responsible of these formulas, okay? So it's the mass times latent heat of fusion. And the latent heat of fusion will be provided in joule per unit mass. So here already it's provided in joule per gram. So I should multiply by the mass in gram to get the corresponding heat in joule. Okay. In this way, I can calculate the amount of heat needed for change of phase. And finally, for the third phase, now once I reach 100% liquid, if I continue to supply heat, then temperature will increase again. Okay. And now what I can say that I have now liquid heating. So also, since it's sensible heating, I use the same formula. To get the amount of liquid heating, I do MC delta T. Now here, they gave me a constant specific heat. In general, the specific heat is a function of temperature. But because here they considered as a constant, so I will take the specific heat they gave me. Okay. So I can say now that in total, in the third phase, I have that Q is M times Cp times delta T. Delta T will be now, I will heat until the pouring temperature. So it's 800 minus 660 degrees. And now, once I calculate the three amounts of heat, I can add them to find the total heat. It's to be noted here that since we considered the specific heat constant, we could have calculated directly the total sensible heat. Because as you can see here, for the first one, it was MC times 660 minus 25. While for the other one, it was MC times 800 minus 660. Since MC is common between the two, then you can see that 660 will cancel out. Because in total, if you sum Q1 plus Q3, you will get MC times T final minus T initial, which is 800 minus 25. Okay, I repeat because I considered constant specific heat. Okay, so now in total, all I have to do is to do the summation. So here you can see the solution in detail. First, we calculated the volume in centimeter cube. This is the volume of the final casting product. But in order to account for shrinkage, the volume of aluminum to be heated should be higher. So they gave us the percentage. So we multiply by 1 plus 5%, which is 1.05. And then to calculate the total heat required, we divided into three steps: sensible solid heating, change of phase heating, and sensible liquid heating. And you can take the mass in factor because it's common for the three parts, which is the mass is calculated as rho times volume. And then I take in factor C delta T1 plus latent heat of fusion plus C delta T2. I get in total 19 megajoule, which is a very large amount. So for example, if they told us gasoline has a heat of combustion of 33 megajoule per liter and has an efficiency of 60%, what will be the volume of gasoline to perform combustion on to obtain this amount of heat? You can do the following. You know that any combustion will not be 100% efficient because we have certain thermal losses. Okay, so when they give us in a problem the efficiency, you can write that efficiency is equal to Q useful heat that will be extracted from combustion over Q total. So for example here, the useful heat is the heat required for aluminum, which is 19 megajoule. So I can write here that useful heat is provided is 19 megajoule and Q total is unknown. I want to find what is a Q total that is needed. Okay, now since the efficiency is provided, it's equal to 0.6, 60%. Then from here I can see that Q total is equal to 33 megajoule. So for example, if I use gasoline, which is characterized by a heat of combustion of 33 megajoule per liter, then I should burn 1 liter of gasoline in order to heat my aluminum from 25 degrees to 800 degrees. So you can see that the amount of heat is really high, and therefore I need a considerable volume of gasoline to achieve this heating process. Okay, any
دكتور
question?
كيف عرفنا إنه 1 لتر إنه 1 لتر؟
عرفنا انه 1 لتر لانه they gave us the combustion heat. يعني نحن اذا بتروحوا على الcombustion combustion gases او combustion liquids على طول بيعطيكم specification اللي هي heat of combustion. Heat of combustion هي how much heat is released per combustion of one a certain unit of volume or mass. يعني هون مثلا if you take gasoline the number of megajoule that can be extracted by combustion from combustion of 1 liter of gasoline is 33 megajoule. So if you want, knowing the efficiency, you have 60% efficiency. So if you burn 1 liter of gasoline, you will only be able to extract 60% of the 33 megajoule. And 60% of the 33 megajoule is 19 megajoule. Okay? يعني أنت what you do, you find what is the Q total that should be provided by combustion. Since you find that Q total that should be provided by combustion of efficiency 60% is 33 megajoule, then you can choose a combustible that has as the combustion heat of combustion 33 megajoule per unit volume, per liter. Now, in case, for example, you have another type, if not gasoline, for example, if you have another combustible for which the heat of combustion is, for example, 66 megajoule per liter. So how much, what is the volume required then? You need to burn 0.5 liter of this combustion, okay?
Okay.
Just depend on what is its heat of combustion. It's a proportional rule. So higher the heat of combustion, lower is the volume required. Okay,
Okay.
so for example, we need 0.5 liter if we considered a combustible of heat of combustion 66 megajoule per liter. Okay, any other
Okay.
question?
دكتور أنا ما باخد هيدا الكورس تبع ما بعرف شو اسمه الترم
Chairman,
لأن أنا
don't
ماني
worry.
ميكانيكال.
Okay, no problem. Don't worry about it. You should know two things. You should know that when I heat a certain system, if it is in one phase, if it is solid or liquid, not a mixture, then the heat provided will raise temperature. And the amount of heat provided is function of delta T using formula Q equal to the mass heated times the specific heat of this mass. What is the specific heat? Is the heat needed, okay, to rise a certain mass by 1 degree, okay? So specific heat
Okay.
is per unit mass per unit delta T. So once you have C, you multiply by the mass in the same unit, of C. And if C is per gram, you multiply in mass per gram. If C is per degrees, you multiply delta T in degrees. That's it. Okay. When you do MC delta T, you get the amount of heat needed to raise your temperature from one stage to the other. Okay.
Okay.
In case you have a mixture, you have solid plus liquid, then the heat provided will not lead to increase in temperature, but will lead to increase in, if you want, energy of the molecules, which will allow them to change from state to state. So whenever I have mixture, I don't have increase in temperature, but I have change in state. And when I have complete change in state from 100% liquid to 100%, from 100% solid to 100% liquid, this means that I have absorbed the total amount of fusion heat, which is provided also in joule per unit mass. So to find the total amount of heat needed for change of phase, you multiply the mass by the latent heat of fusion. We call it latent heat of fusion when we go from solid to liquid, and we call it solidification heat when we go from liquid to solid. And it is the same amount, of course, but when you are heating, you are gaining energy, you go from solid to liquid. When you are in the solidification process, it's the opposite. You are releasing back this heat, so you go from liquid to solid. Okay.
Okay, so only these two formulas I need to
Yes,
know.
only these formulas. And you have them in the formula sheets I already provided you. They are summarized also in the formula sheet for you.
Okay, thank you, doctor.
Welcome.
Doctor, I have a question.
Yes.
But can you repeat the equation تبع phase 2 latent heat?
Yes, of course. In phase 2, you have change of phase. Whenever you have change of phase, the heat is provided by the following formula. Heat Q is given by the mass that is changing phase times what we call latent heat of fusion. Fusion, when we go from solid to from solid to liquid. So here you are heating your system. Then energy absorbed by solid state will be transformed. This energy will allow molecules to get far from each other and to go from solid to liquid state. So whenever you complete your fusion process, you go from 100% solid to 100% liquid. The amount of heat provided should be equal to the latent heat of fusion, which is provided in joule per unit mass, times the mass which you are heating, which is in gram. By doing this product, you get the amount of heat in joule required to change phase from 100% solid to 100% liquid.
Okay, doctor. Thank you.
Any other questions? Okay, guys. So we continue these problems next time, or maybe I think for next time I will give you recorded PowerPoint of chapter 8. And then we can continue together on Fridays the problems. This will give you time if you want to try to solve them. Okay, they are posted on Blackboard already in problem sections.
Okay, thank you, doctor. Bye.
Doctor, can you post this session, the recording of this session, you know?
Yes, of course. I'm always posting them. Yes.
Because I had a lot of electricity problem today. I don't know why.
Okay,
Sorry.
look, if you watch it again and you still have problems, I can repeat it for you. So you can ask me next time, okay?
Okay, thank you.
You are industrial engineer?
Yes. Yeah.
Okay, maybe this is why. Don't worry. You are just supposed to know these two formulas, not more. Okay? If you
Okay.
still
Okay.
face difficulties, you can ask me next time your questions.
I will. Okay. Thank you.
Okay, welcome. Bye. No, you can, of course, you can send me WhatsApp if you want something, of course. Yeah. Bye.